So we're going to start on section 1.2 today. This first chapter is all about functions. So functions in general and how we analyze functions. So we'll be talking about domain and range, increasing, decreasing, local maxes, local mins, the different families of functions. We'll also be getting into transformations, which is going to come up again and again and again this year. We talked about some of these prerequisite skills, interval notation, on Wednesday. And if you weren't here, that video is on Canvas at this point. We did graphing on a number line, solving equations and inequalities. We're going to look at a little bit today. Factoring we should be good at. So we're going to go ahead and dive right into the new stuff. So first of all, let's define what a function is. A function is just a rule that pairs an input with at most one output. So the big rule is a function cannot have more than one output. An input, cannot have more than one output. Another way to define a function is, can you write it as an equation that says y equals, but this is the formal definition. So some of the problems on your assignment today are going to ask you, they're going to give you some equations and they're going to say, is y a function of x? When they use this language is assuming that this is our input and y is your output. So is y a function of x? This one says y equals 2x, and it's already written in y equals form. The question we would have to ask ourselves can you think of a value of x that would result in more than one different values of y? For example, if I plug 0 in for x, am I going to get two different values for y? Is that possible? No. So yes, this is a function. On your assignment for those problems, you can just say yes. Second one, is this a function? Can you think of a value of x that could give you two different values of y? An input that gives you more than one output? Give me an example. 1. If I put 1 in for x, this says that the y value would be 1 plus 1 or 1 minus 1. So y could either equal 2 or 0. So for a single value of x, we have found two resulting values of y. One input gave us two outputs, so no, this is not a function. Part C is not written as a y equals equation. Could you write it as a y equals equation? Pretty simply, yeah, we could solve for y. We could divide by 3 on both sides and write it as y equals x over 3. Is that a function? Are there any x values that could give you more than one y value? Not for this one. What type of graph would this make? Y equals x over 3. Another way to write that would be y equals 1/3 x. What shape would that graph be? What family of functions are we looking at here? That would be a linear function. Yeah. So yes, this is a function. Last one. X equals y squared plus 1. Could we easily solve for y in this one? Kind of, yeah. We could do minus 1 on both sides. That would get us x minus 1 equals y squared. And then we could square root both sides. What happens? What do we have to remember to do when we square root both sides of an equation and we're square rooting variables, though? Did you guys learn this last year? I know for a fact you did. You have to include both the positive and the negative versions of that square root. So is that a function? No. Can anyone think of a x value that would give us two different y values? Any of them? Yes. Give me a specific example. I heard 5. So if I plug 5 in for x here, we're going to have 5 minus 1, which is 4. We'll take the square root of 4, and that would be 2. Or if we did the negative version, we would get negative 2. So no, it is not a function. So in your assignment, you're going to get a list of equations. They're going to say, is it a function, yes or no? If no, why? And to justify why it's not a function, I'd like you to just find me one value of x. It'll give you multiple values of y. Good? Any questions on that so far? This should be kind of review-ish, maybe. All right. We're not going to go over the vertical line test because I think you guys have seen it plenty of times. Why don't we do this? Can you draw me, right in this space here, draw me two x, y axes. And can you draw me a graph that would pass the vertical line tests and a graph that would fail the vertical line tests? One that would pass and one that would fail. The notes are in the back of the room. Sorry about that. I didn't notice. You're missing those. I'll give you mine at the end of class so we can get you caught up on the stuff you missed. One that would pass, one that would fail. Like that. Got some nice. We'll get some. I saw several people drew some form of a parabola for the past one. It doesn't have to be a parabola. It could be a line. It could be an absolute value. It could be a cubic equation. The important thing is if we draw a vertical line anywhere on this graph, it is only going to intersect our function in one place. Okay, if you haven't already, please draw me a fail graph. This would be a graph where a vertical line somewhere on the graph would cross the graph in more than one place. Yours might look different from mine. Probably will. And I want you guys to do some thinking about the vertical line test and how it relates to that rule that we were just applying a moment ago. Algebraically, we said that something is not a function if a single x value results in more than one y value. How does that relate to what you see visually going on here? I told you guys on Wednesday that this class is a lot more about making connections than it is about just being able to do steps. This is the type of thinking that is going to be required of you if you're going to get an A in this class. So what is the connection between the rule that an input or x value cannot have more than one output or y value? What is the connection between that rule and what you see going on in that picture? I'm going to give everybody a chance to think about it for a couple more seconds, and then I'll call on you. Thank you, though. Appreciate it. Just a sec. Thank you. I appreciate it. How would you describe the connection? Okay, I like that. I like that you were talking about tables. So if I made a table for this, an XY table, and I just tabulated these 3 points, what would you see for in the X column for those 3 points? They'd all be the same. These points are stacked on top of each other. The X coordinates should all be the same. But what about their Y values? The Y values would all be different. Did you want to expand on that? Okay. Good, good. So you're kind of thinking about the coordinate pairs, the points? Yeah. Yeah, same idea. If we were to look at the x and y coordinates for these, the x's would all be the same. The y's would all be different. Okay, we talked a little bit about domain and range on Wednesday. Domain goes with input or x values. Range goes with output. We're not going to be doing much with range in this first chapter. We'll be looking at range algebraically, or I'm sorry, graphically. But our main thing that we're going to do today is finding the domain of a function algebraically. So we're getting into like the key part of our notes today. So focus and make sure that you're asking questions if we run into anything that you don't understand. All right, when it comes to finding the domain of functions algebraically, what we need to do is we need to look at the equation of the function, and we have to ask ourselves the question, what could break this function? You guys have learned some rules about math, some things that we are not allowed to do in math. One of them involves fractions. What is the big rule about fractions? What can we never do with a fraction in algebra? We can never divide by 0. There can never be a 0 on the bottom of a fraction. That breaks the fraction. That is undefined. So the first thing that we're going to look for is, does our function have fractions? And if it does, we need to say that the denominator must be what? Must be, I'd say, not 0. Not equal to 0. This is our restriction for any fractions in a function. The denominator must be not equal to 0. That's kind of awkward to say in English, but it's easier to deal with mathematically, okay? All right, so let's work through a couple problems here. We're going to find the domain for this first function in part A, and we're going to look at it. We're going to notice that it is a rational function, meaning it has a fraction, and our eyes are going to go right to that x minus 1 on the bottom. And I'm going to make myself a note that the denominator cannot equal 0. And then I'm going to write down my restriction. So for this function, if the denominator cannot be equal to 0, then x minus 1 cannot be equal to 0. Could you please put a box around that and a star next to it? If this problem were on the test, that statement right there would be worth points. If you did not write that statement, even if you got the correct final answer, you would be missing points on this. I need you to write down the restriction. We're going to practice this, and I'll point out these things that I'll be looking for. Now, this part up here, do you need to write this on a test? No. Would it be a good idea to write it on your assignments? Why would it be a good idea to write for every single problem that you do with a fraction, denominator not equal to 0? That seems like an awful lot of repetition. Why would you ever want to repeat something over and over and over again? You guys know where I'm going with this, right? So you remember it. Okay. X minus 1 is not equal to 0. I don't know if you guys have solved a lot of equations that look like this, but it's just like solving a normal equation. So we would do our algebra steps for this. I told you guys you don't have to do this, but I'm going to go ahead and do it for this first one. Minus 1 on both sides, and we get... Oh, thank you. Add 1 on both sides, and we get x equals 1. X not equal to 1. So we've simplified our restriction, and now we're going to write the domain of this. Remember, the whole point here is to find the domain, the x values that can go into this function. We have found that there's only one x value that cannot go into this function, and it is 1. So to find this, I like to do a number line graph because I'm going to ask for it in interval notation, and this just helps me to get things in interval notation. I always put 0 on my graph. I'll put 1 over here. If x is not equal to 1, that means it's everything else. So we're about to write down our final domain. This is what we practiced on Wednesday. See if you can do this last part on your own. Can you write interval notation for that line graph on your own? I see 2 separate intervals there. Don't forget to put that union symbol in between them. All right, and there's our first one. Any questions on that first one? Okay. I told you on Wednesday I believe in transparency on my assessments. I want to show you what I would grade if I were grading this as a test item. I would be looking to see that you had this on your paper, that you had this on your paper, and I would be looking at your final answer. Those would be the pieces that I would be grading. Okay. The line graph, it's up to you. We're gonna have some that are gonna be pretty simple, and some of you are gonna decide I don't need to do this, but we will have some that'll be quite complicated, and we'll actually look at one of those today. And this graph will be very, very helpful to you. All right. Can you take a moment and remind yourself, what are we doing here? What were we trying to do when we came up with this final answer? We're trying to find what? Find the domain. Find the domain algebraically. And what is the domain again? The domain are the x or y values. They're x values. The domain is the x values that are allowed to go into this function. Okay, that's what we're doing here. So if I asked you, for instance, am I allowed to put -2 into this function? Am I allowed to put -2 into this function? Yeah, it's part of the domain. It'd be in this region right here. Am I allowed to put 17 into this function? Yep. Am I allowed to put pi into this function? Yep. Can I put 1 in this function? No, that's not part of my domain. That would break the function. Okay. So this is going to be an important thing in this class, and again, I said this is going to be a bit of a shift for you as you're working your problems. Make sure you remember what is it that we're actually trying to accomplish here. So that later on, when we have to use this as a small part of a much bigger problem, we remember, like, what does it mean to find the domain? Okay, let's do another. This one has 2 denominators. Oh my goodness. I see 2 denominators. And I am just going to remind myself, denominator cannot equal 0. And I'm going to write my 2 restriction statements. Since I have 2 denominators, I'm going to have 2 restriction statements. One is going to say x plus 1 is not equal to 0 because that was one of my denominators. And the other one's going to say x squared minus 4 is not equal to 0. And remember, those are key steps there. Make sure that you're writing those down. A lot of you are going to be able to look at this and say, oh, x is not equal to -1. That's great. Don't show off, though. Write down the restriction and then go from there. All right, solve this. -1 on both sides. We got x not equal to -1. X squared minus 4, how do we solve that? Factor it. X plus 2x minus 2. Use your zero product properly. Split it up into 2 equations. And then solve those. There is another way to solve these. Might be a little bit quicker. From here, I could have gone x squared equals 4, and then take a square root on both sides. You would get x not equals plus or minus square root 4, or x not equals plus or minus 2. So far, so good. Make me a graph of what that would look like. I got more space over here. I'm going to put it over here this time. Let's see. We're excluding 3 values this time. -1, -2, and 2. And go ahead and practice your interval notation skills with that one. I encourage you to do as much of this part from here on your own as you can. I'll put my answer up here so that you can use it for a hint or check your accuracy, or check my accuracy. This is a messy one. There is a much easier way to write this, and when we get to chapter 2, I will give you permission to write it that way. I am going to ask in chapter 1 that we write all of our answers in interval notation, just so that we get so good at interval notation, when it comes up again later, we don't even have to think about it. Okay. Chapter 2, we would just write all real numbers except -2, -1, and 2. And it's going to save us whole seconds of our lives. All right. We good so far? You guys feeling all right? Show me on your thumb meters how you're feeling today. Show me on your thumb meters how much energy you have today. The third day of school is always the hardest, right? The first day you're like living on adrenaline. Second day, still kind of like getting into things, and then day 3, you're like, oh. Thank goodness. I love this though. We have the 3-day, and then you get a 3-day weekend, and then next week's only 4 days, so we kind of work our way slowly up to the full week. So we'll get there. We'll get there. All right. There's something else that breaks functions. Actually, there's a lot more things that break functions and fractions, but we're going to focus on just 2 for right now. We'll add more in later throughout the year. The other thing that can break functions are square roots, specifically even numbered roots. And you guys have learned some things about this. Now, when we say functions, when we're dealing in functions, we're dealing with real valued functions. We will never get imaginary or complex values out of a function, okay? So what is the thing that can cause us problems with square roots, that could cause us to have not real value? You can't have negatives inside of a square root, okay? Now, the inverse of that is easier to do mathematically. It's just harder to say in English. So the inside of the radical must be what? What is the opposite of it can't be negative? It must be positive or equal to 0. Yeah, so it must be greater than or equal to 0. So positive, or it could be 0. You can take the square root of 0 and get a real answer. So greater than or equal to 0 is our restriction for radicals. By the way, the thing inside of a radical is called the radicand. All right, so let's do an example here. I look at this and I don't see any fractions, but my eyes go to this radical here. Like, we're going to have to deal with some restrictions because I have some x's inside here. We need to ensure that this thing's not going to give us any, it's not going to break the function. So what's our restriction? Well, radicand must be greater than or equal to 0. I'm writing that down, and I encourage you to write that down for every single problem. It's going to help you remember it when it comes up again in Chapter 3 and Chapter 7 next year in calculus. The radicand must be greater than or equal to 0, and our radicand this time around is 1 minus 2x. So we'll go ahead and simplify that, solve that, get that x by itself. And do a little bit of algebra here. So what do you guys want to do first? Minus 1 both sides? All right, minus 1 both sides gets us negative 2x greater than or equal to negative 1. Is it bothering anybody right now that I'm not writing that minus 1 on both sides? You guys okay with that? Okay, you're going to get used to that over time. If it helps you to still do that, you're more than welcome to. I need to get rid of that negative 2 that's multiplying, so we'll divide by negative 2 on both sides. And what happens when we divide both sides of an inequality by a negative number? We've got to flip the sign. Did you guys remember to flip the sign? So negative over negative is going to be positive 1/2. So x is less than or equal to 1/2. So there's our restriction. I'm going to go ahead and graph this. Less than or equal to, so that gets a solid dot, closed dot. If x is less than, then we're heading to the left. And then we just need to turn that into interval notation. I'm going to leave that one up to you guys. You are going to have a square bracket this time around. Questions before we move on? You guys are doing awesome. All right, I'm going to cruise through this next one. A C. This is a fourth root this time, and it's really the even numbered roots that cause this problem. If this had been a cube root or a fifth root instead, there are no restrictions for cube roots and fifth roots. You're allowed to take the cube root of a negative number. You're going to get a negative result if that happens. Fifth root, seventh root, same thing. So fourth root, that doesn't matter. What matters is that it's even. We've got a radicand, and we need to make sure that that radicand stays greater than or equal to 0. As long as the radicand is greater than or equal to 0, we're going to get an output. So we know that x squared minus 25 must be greater than or equal to 0. And we need to solve this inequality. Now, solving an inequality that has a higher degree than 1, you can't just do plus 25 on both sides and take a square root on both sides. That doesn't work. It works for equals. It does not work if it's less than or equal to, greater than or equal to. There's a way to do this that involves sign charts. I'm told you guys spent like maybe a day on sign charts last year. We're going to spend a day on it later on this semester. The way I'm going to solve this for right now, though, is I'm going to graph this as a function, just the x squared minus 25, not the whole function, just the x squared minus 25. So I'm going to look at this and say, I'm going to think of the function y equals x squared minus 25. And I'm just going to make a quick sketch of this. Now, if I want to make a good accurate sketch of this, I should know where my y-intercept is and where my x-intercepts are. And again, my hope is at this point, within a matter of 30 seconds or less, you can look at that, find your x-intercepts, your y-intercepts, and make a fairly accurate graph of that thing. Practice that a little bit in your assignment. Where would my x-intercepts be? Might help to factor it. So -5 and +5. So we're going to have x-intercepts at -5 and at +5. And a y-intercept. How do we find the y-intercept for any function ever? Put 0 in for x. If you put 0 in for x here, you're going to get y equals -25. All right, so that's a parabola, opens upwards. Crosses the x-axis at -5 and 5. Okay, this is a skill that if you're, again, this is one of those things. If you're not comfortable with what I just did right there, please schedule some time with me next week or in the next couple of weeks, and let's get you feeling good about that. Okay. All right. Why did I do that? Because ultimately, I want to know where that x squared minus 25 is greater than or equal to 0. This is kind of why we practiced this on Wednesday. Greater than or equal to 0 means are we talking about above or below if it's greater than or equal to 0? We're talking about the regions where it's above. It would be above in this region here and in this region here. Or equal to. So we're also going to include that point and that point here. So any of those x values that I just highlighted in green and darker are going to make this true, which means they're part of our domain. So can you turn that into interval notation? If it helps you to draw a little number line down here, feel free to do that. And let's write our interval notation, final domain for this. You're going to run into one or two problems where you're going to have a quadratic inside of a radical. You'll basically follow the same process. Turn it into an equation, just the quadratic part. Make a quick sketch of it by factoring it. And use that sketch to figure out where is it going to be either above or below the x-axis. I'm guessing you'll probably be above the x-axis because it's always greater than or equal to 0. Remind me, what are we doing here, this whole page? What's the point of all this? Finding the domain. And why is the domain important? Because those are all the x values that are allowed to go into a function. If I asked you for this particular function here, is it okay for me to put 3 into this function? Is 3 part of this domain? No, it's not in this interval, it's not in this interval. So 3 is no good, but what about 7? 7's fine. -5? Yeah. -5, well, it's right on the edge, but it works because of that bracket. Okay, that's the point here. Now, for right now, all you need to worry about, all that you're going to see when I ask you to find domain algebraically, you'll see problems with fractions, you'll see problems with radicals. If you don't see a fraction or a radical, then the domain is everything, all real numbers, -infinity to infinity. For now, we're going to add on to this. In chapter 3, we'll be looking at logarithmic functions, so we'll be adding some different restrictions for log functions. Inside of a log has to be greater than 0, not greater than or equal to, strictly greater than. Next semester, we'll learn about tangent, secant, cosecant, and cotangent functions, and those all also have restrictions for what's allowed to go into there, but you're not going to see that for right now. We just need to look at fractions and radicals. So let's do this one. You guys are doing awesome. And this is our last problem for today. The rest is going to be, we'll cover next Wednesday. So here we go. This is, oh man, look at this. So this is by far the most complicated problem that you're going to see of this type. and we're going to do it together. I would never put something like this on a test unless it was a bonus. You won't see anything nearly this complicated in your assignment, so don't get freaked out if it gets a little messy, okay? I gave you half a page for a reason here. We got a lot going on here, a whole bunch going on. It's okay, though, because we're going to deal with it one little piece at a time. So there's two important things that we have to look for when we're looking at functions and we're thinking about domain. There's two things that we need to worry about breaking. Which one you guys want to deal with first, the fractions or the radicals? You want to deal with the radicals first? We can do that. All right, let's focus on our radicals. Now, do we need to worry about this radical? It's a cube root. Nope, cube roots are all good. You can't break a cube root. You can put any number you want into a cube root. So we're not going to focus on that, but I do see an even root here, and I see another one here. So I'm just circling the insides, the radicand, because I know that my radicands must be greater than or equal to 0. Those of you who write out that word radicand greater than or equal to 0, you're going to get to the test and you're not even going to have to think about it. Wait, was it not equal to 0, greater than or equal to 0? You'll have it down. Now we're going to need two different inequalities because we have two different radicands. So 2 minus x must be greater than or equal to 0, and also x plus 3 must be greater than or equal to 0. And we will solve those two inequalities. Again, please remember that I have to see that restriction step. I need to see the thing that came from the function either not equal to 0 or greater than or equal to 0. Okay, don't be skipping this step because this will be worth points on the test. All right, go ahead and do a little bit of math and solve those two things. Get x alone. You might be dividing by a -1 in one of these, which means you might have to flip your inequality. So we're going to take this result and sort of stick it in our back pocket for right now. We'll come back to it when we finish up the problem as a whole. Let's deal with the other potential problems. This function does contain a fraction, and so we're going to need to deal with that as well. I am circling the entire denominator because it's the denominator that could potentially cause problems. Does anybody have any questions about that? I'm sure a few of you do. Well, we'll keep going and maybe the question will come up. What's our rule? Our rule is that the denominator must be not equal to 0. So x minus 1 times the square root of x plus 3. That was our denominator. That must be not equal to 0. Pause here for a second. See if anyone has any questions. Oh, come on. No question? I'm waiting for somebody to ask a really good question right now. Can somebody, even if you don't have this question because you know the answer, can you tell me what question I'm waiting for right now? Yes, thank you. Yeah, what a great question. Didn't we already deal with this square root? Didn't we already deal with this over here? Why did that have to be in there again? Does anybody know the answer to that? Because it's multiplied to this? Kinda. What do you think? Because it's part of the denominator. The rule is that the denominator must be not equal to 0. Okay, we have dealt with a portion of the denominator already, but we haven't dealt with the entire denominator, and we have to deal with the whole thing. Okay, just because it had a radical and we've dealt with the radical doesn't mean we get to ignore that portion of the denominator. So when we do this, the entire denominator, even if it's got something that you've already dealt with or that you're going to deal with separately, has to be not equal to 0. And we're going to solve this. Now, does anybody have any follow-up questions to that? I'm anticipating some more, but maybe we'll finish this up and come back because it kind of gets into the weeds. All right, so let's solve this. It is multiplying, and that's key because if I have two things multiplying and equal to 0, what am I allowed to do with those two things? I can split them up and set them each equal to 0. That's that zero product property. And you guys know that only works if those two things are multiplying and equal to 0. If that had been a 5 over here, we're not allowed to do that. Now, you probably maybe haven't seen this applied when it's not just like two factors, but it works with any two things that are multiplied and equal to 0. And then we'll solve these two things. So this one's easy, plus 1 on both sides. X isn't equal to 1. How would you solve this one? How would you get rid of the square root? Yeah, square both sides. That would give you x plus 3 not equal to 0 squared is still 0. And then minus 3 on both sides, and we got x not equal to negative 3. All right, we doing okay? We're about to pull this all together and get our final answer. Are there any questions before we do that? Timing is going to be perfect. All right, we need to put that's together. I'm going to think of this as kind of one big thing, and then I'm going to graph these two things separately. So let me get a number line going, and I'm going to leave a significant amount of space above my number line. Yes? Can you say that again? I'm sorry. If we knew that if the denominator part was, I'm not understanding.
I think what she's noticing is that when we did the math for the radicand, whatever the thing is called.
The radicand?
We got x is greater than or equal to negative 3, and we also got x is not equal to negative 3. It's the same numbers. So
yes. Okay. Yes. That is the follow-up question I was talking about just a second ago. Okay. So can I finish this up and then we'll come back to that question and don't let me forget. Okay. Because I'll get really excited here at the end of this and then I'm going to forget. Please don't let me forget. Okay. We will come back to that. Was anybody else thinking that same thing? Like negative 3 was here. Can we just like take this and get rid of the little or equal to underneath there and we'd be fine? If anybody else is thinking that, yes. Yes, you can, and we'll talk about it in a minute here. I'm going to go ahead and finish this up, though. So I'm drawing my number line. I'm going to put 0 in the middle. And then, I'm sorry. I'm going to put 0 in the middle. I'm leaving space above it because I'm actually going to have 3 line graphs stacked above it. And I'm going to get my important numbers on here. It looks like 1 is an important number, 2 is an important number, and negative 3 is an important number. And I am going to make 3 line graphs. I'm just going to stack them on top of each other, one for each of these restrictions that we came up with. So the first one was x is less than or equal to 2. So we need a closed dot at 2, and less than goes this way. And then up above that, I'm going to graph this one. X is greater than or equal to negative 3. So negative 3 gets a closed dot. And the graph goes this way. And then this one, we know what those look like. This is just going to be everything except it's going to have a couple of open dots in it. Open dot at 1 and another one at -3, but everything else is filled in. So my final domain is going to be the intersection of all three of these graphs. It's going to be anything that's covered by all three of the graphs. Okay, so I'm going to kind of start from the left to the right and ask myself, are all three graphs overlapping? So are all three graphs overlapping in this region right here? All three of them? I see one of them, two of them, but not this one. So not here. What about at -3? Are all three overlapping at negative? Oh, we're missing almost all three of them. We're missing that one point. What about right in here? Oh, I see 3 overlapping there. So we're going to have domain in this area. We said not at -3, so let's go ahead and put an open dot there because we didn't have all 3 overlapping there. And they continue to overlap as we move to the right. What's the first place that we don't have overlap of all 3? At 1, we miss out with that top one there, so we're going to need an open dot at 1. And then we're overlapping again between 1 and 2, right? And how about at 2? Are all 3 of them overlapping at 2? So we need a closed dot there. And then from there we can write our final domain. And I was excited, but I did remember your question, and we're going to come back to it now. Or shortly. Pause for a moment and ask yourself the big important question. What did you just do? What was the point of all that work? Did you answer your question in your head? What was the point of all this work? What were we trying to accomplish? Trying to find the domain. What's the importance of finding the domain? We've found all of the x values that can be input into this function. If I look at this and I ask you the question, can 0 go into this function? Yes, 0 is part of my domain. Can 17 go into this function? No. Okay. All right, let me go back to your question here. When I used to teach this, I used to teach that there were a lot of different rules for this, okay? So my rule when I started teaching this was that factors in the denominator are not equal to 0, but if you have a radical in the denominator, then it's greater than 0, but if it's in the numerator, it's greater than or equal to 0, okay? And what I found is that that was way more complicated than it needed to be. It's a lot of stuff to remember. Now, if your brain is, if you saw that and you're like, oh, that works for me, then that's okay. I'm okay with that. I would prefer, I'm the type of person that if I can take 5 or 6 rules and simplify them down into 1 or 2 simple things, my brain's going to remember that for longer. It's going to be easier for me to pull off. So I don't worry about, like, I'm not going to look at this and look at this radical any differently than I look at this radical, because the fact is that the radicand has to be greater than or equal to 0. And as long as I include this radical as part of the denominator, the fact that it can't actually be equal to 0 is going to end up in here anyways. And I can trust that math that that's going to end up coming out of it, so that I don't have to remember those extra steps. Does that kind of answer your question? So that's why, and it's awesome that you're making that connection and you're recognizing that those two things are connected. But I do it this way for 2 reasons. One, it is the mathematical principle behind it is simply the whole denominator can't be 0, and the radicand has to be greater than or equal to 0. And secondly, it's just simpler for me to deal with it that way. Okay? Any other follow-up questions? Thank you guys for those questions. I appreciate it. It is time. Okay. Part of your assignment is to do some self-study on page 95. I'm going to give you on Tuesday a little non-graded quiz just to make sure you guys understand what boundedness and continuity is. Folks, this is going to happen a lot in this class. We don't have time to cover everything that you need to know. You're going to have to learn some of it on your own. These are two simple concepts. You spend 5 minutes reading and looking at those examples, and you're going to understand it. And then I'll take questions on it on Wednesday. Just that. And then the rest of the packet we're going to do next Wednesday. There's an assignment on Canvas in case I should have time to go over that still. At this point, guys, we're not leaving. Don't put your stuff away just yet because we're just going